Assalamualaikum and very good evening to all of you. Welcome back to our class, the BAA2213, the reinforced concrete design. Today we will enter the new topic, which is the design of reinforced concrete column by referring to Eurocode 2. Okay, by the end of the lesson, by the end of the topic, here is the list of lessons you must conquer, which is first, you must be able to identify the column type, and then you must be able to define and explain the column loading, as well as to calculate the actual column loading, and then you must be able to design typical simple column, and you must be able to illustrate the simple column detailing. For these two these last two, we can go to the example by the in the module. Okay, what is column? Column is a compression member. Okay, so this is the keyword compression member, which is usually carried the load from the beams and slab and transfer it to the foundations. It caters the axial load and bending forces due to the continuity of the structure. By refer to the clause of 5.3.1 in bracket of 7 in Eurocode 2, column is a compression member. Okay, the keyword is compressions, where the greater cross-sectional dimension does not exceed 4 times the smaller dimensions, which means that, let's say we have a rectangular sections B and H. Let's say this is the B and this is H, so the H is not exceed, okay, this one, H must not exceed 4 times of B. If H is greater than B, let's say this one, okay, H is greater than B, maybe the definition, okay, will form the wall, okay, the shear wall. Okay, and then the height of the column must at least 3 times the section depth. Okay, at least 3 times. Let's say this is the depth of the section and must greater than 3H. Okay, and columns it can be divided into 2 categories, which is the braced columns and the unbraced columns. Okay, for the braced column, the design will only, okay, the braced columns will only consider the axial force, because the lateral loads are resisted by the shear walls or other form of bracing capable of transmitting all horizontal loads to the foundations. For the unbraced columns, the horizontal loads are resisted by the frame actions of rigidly connected columns, beam, and the slab. Okay, if we look for this to these figures, so we have the shear wall here. Okay, this is the plan view. We have the shear wall here at the edge of the building. So this is the column here is categorized as the braced columns, where the lateral stability at particular plane are upheld by the restraining walls. So the N, okay, the axial force and the bending moment are induced by axial load only. Okay, either the shear walls is located at the edge or at the middle of the plan. Okay, for the unbraced column is like this one. Okay, there is no shear walls, so the lateral stability is only upheld by the columns itself, okay, without any other bracing elements. The load arrangements need included the effects of horizontal loads. Okay, and there is the 2 types of column. First is the, okay, either the slender or non-slender column. For the short columns, the fail will be by the crushings or, okay, due to the compressions. And for the slender column, the fail is by the buckling, okay, to do the action of bending. Okay, and this video shows the typical column failures, where we can see that the concrete is okay, the buckling of steel reinforcement, and then the crushing of concrete core. Okay, and this is the design procedure for the column. Okay, step by step, number 1, 2, 3, 4, up to 9. Okay, and the number 1 to number 6 is the checking, and this number 7 is to determine the final design moment, and number 8 is the design process. The detailing is the step number 9, and this is the corresponding standard or rules to be referred. And okay, axial loads and moment in column. Okay, the axial load and the moment is obtained through the subframe analysis. Okay, for the column given design, for a full frame analysis follows procedures as the given below. Number 1 is we assume that the beam and slabs are simply supported. Okay, this is on how to determine the axial load or the N. Okay, thus the axial load is equal to 110% times the load obtained. This is the by condition that the adjacent spans and or the loadings on them are more or less similar. And then the bending moment is obtained from simplified one free joint subframe. Okay, this is the conditions in order to check for this is the condition. This is the condition to determine the axial force. Okay, this the condition of loading. I mean the load arrangements. Okay, we assume that let's say we want to design this column. Okay, sorry. If we want to design this column, okay, the green color. Okay, we want to design this column. So in order to determine the value of N, the axial force, so we arrange the loading as this one. Okay, maximum loading for both. Okay, side beam. Okay, this beam from the left and then this the beam from the right. On both sides, we must consider the maximum axial force. And in order to determine the bending moment, so we arrange. Okay, this is the arrangement of loading. Okay, maximum. Okay, this is the minimum and maximum. So this maximum side. Okay, the maximum condition of loading will cause the column to bend in these directions. Okay, and then the column design involve the considerations of these following aspects, which is the slenderness ratio, slenderness limit, first order effects, second order moments, and then the reinforcement details. Okay, for the first one, which is the slenderness ratio, it can be determined by using these equations where the L0 is the effective length and I is the radius of gyrations. And the effective length, okay, we can refer to these equations, okay, equation 5.15 and equation 5.16 from Eurocode 2. Okay, and the value of K1 and K2 are the relative flexibilities of rotational restraints at N1 and N2. Okay, and then okay, we can refer to this table later in the example or the tutorial. We can I will explain on how to use this how to refer this table. Okay, what is the condition number 1, condition number 2, condition number 3, and condition number 4. Okay, and this is the explanations of all 4 conditions. And then this is the slenderness limits. Okay, you can use these equations. Okay, the slenderness limit is important in order to classify the column. Either the column is under category of short column or slender column. Okay, if it below the limit, so the column is short column, and if the slenderness ratio is greater than the limit, so this one is slender column. However, for this syllabus, we only cover the design for short column. Okay, and this is the moment due to imperfections. We can take a look later in our tutorial. Okay, and this is the minimum and maximum reinforcement. This is the design part for this class 9.5 in Eurocode 2, page 162. So the longitudinal bars, okay, the value of longitudinal bars means the vertical bar. Okay, the vertical bar. Okay, let's say this is the column cross sections. Okay, okay, let's say this is the main reinforcement here. 1, 2, 3, and 4. Okay, the diameter shall be okay, the recommended value is 8 mm. Okay, this is the maximum. Okay, greater than 8 mm. Okay, not less. Okay, not less than diameter minimum. Okay, diameter, so 8 mm is the minimum. The total amount of longitudinal, okay, this is the limit. Okay, as minimum shall be derived by these equations, or 0.002 AC. AC means this one. Okay, this is the, let's say this is the B, this is the H. Okay, so 0.002 times B times H. This is the limit, the as minimum. Okay, and this is the maximum is must be, okay, should not, longitudinal reinforcement should not exist as maximum. So as maximum shall be 0.004 AC. So maximum, this is the minimum. The maximum cannot be greater than 0.04 times B times H. Okay, and at the lab, let's say this is the lapping. It's okay, this is the starter bar, and then you have to consider the lapping here outside the critical region, and you want to do the lapping here. This is the lapping. So here at the lapping, the allowable limit is maximum is less than 0.08 AC. So AC means B times H. Okay, and so this is the arrangement of reinforcement for rectangular column. We must provide at least 4 bars. Okay, and for circular column, okay, 6 bars. Okay, the better is 12 mm. Okay, 12 mm is better for vertical reinforcement. Okay, this is the example of arrangement of shear links and ties in square and rectangular columns. Okay, the dot here is the vertical, and then this is the link or the ties. Okay, and then this is the design of link. Okay, we must the diameter here, the diameter is shall be not less. Okay, not less means shall be greater than 6 mm, or 1/4 of the maximum diameter of longitudinal bars, whichever is greater. So you must select the diameter. You must select, maximum. Okay, select maximum either 6 mm or 1/4. 1/4 means by 4. Okay, let's say the vertical, let's say the size of diameter of main bar is equal to 20. Okay, so 20 divided by 4 mm. So you select the maximum is 6 or 12. Okay, this is 5. So in this condition, you select the maximum, the minimum shall be the 6. So you can use, let's say, diameter is equal to 10 mm. Okay. And then the spacing. So this one, the spacing maximum is maximum spacing. You must select value is the least. The least means the minimum. Okay, you select the minimum between these three. 20 times the minimum diameter of longitudinal bars. Okay, 20 times the diameter of longitudinal bar. And then the lesser dimension of the column, the lesser between between H. Okay, lesser dimension, you may B or H. Which one is the lesser? And then 400. 400 is the limit of spacing for column. It's okay. We will take a look this one in our tutorial. We will refer to the tutorial later. Okay, and this is the column design charts on how to determine the value of, okay, the value here is ASFYK over BHFCK is equal to what is the value is we determine from this chart. Okay, I will show you later during the tutorial. Okay, and this is okay, design chart is usually used for columns having a rectangular or circular cross sections and a symmetrical arrangement of reinforcement. For the unsymmetrical arrangements, so the basic equations can be used. Okay, class. Now I will explain about the biaxial bending for column design. Okay, so we must check the biaxial bendings. Okay, if it means that the column will bend in two directions for to the major or to the minor axis. Okay, let's say this is how to determine okay the H value of the column. Okay, if the column is bent, okay, let's say this is we have the major axis of Z Z and Y Y. Okay, and then we have a rectangular column with the dimension of B and H. So we must look where is the direction of the bending, either about the axis of ZZ or about the axis of YY. Okay, let's say, what if the column is bent around the major axis? Major axis is ZZ. Okay, let's say this is the axis, and then it will bend to these directions. Okay, let's say here this is the axis of, okay, this is this is Z, and then this is the Y and Y. Okay, so it will bend. Okay, the bending will go to, okay, around. Okay, that means the axis is Z. Okay, let's say this one. Okay, this is the column. Okay, this is okay, let's say this is direction. Okay, this is direction number 1. Okay, this is direction number 1. So, and this is direction number 2. This is direction number 3, and this is direction number 4. So just imagine that we are looking from direction number 1. Okay, we are looking from, this is the plan view. This is the plan. This is the side view. Okay, the side view or elevation view, and this one is the plan view. Okay, if we look from here, from direction number 1, so this is what we will see. Okay, this is the column, and this is direction number 3 here. If we stand here, okay, we look to the column, then this is direction number 3. And if we are standing here, we look to the column, and this is the direction number 2. Okay, so it will bend. Okay, this is the ZZ axis, and then this is the Y axis. So it will bend. Okay, it will rotate through the Z axis. So let's say this one, it will rotate. It will bend like this one. The column will bend along, okay, the Z axis. If we see from number 1, if we are stand here, the column is bent to the, now it bend to the left, to direction 2. Or it is still possible if the column is bent to the 3. Okay, this is the end. This is the axial force, and this is the bending moment. Okay, this is the there is the bending moment. Okay, it will cause the, okay, if the bending moment is go to here, it is clockwise. Okay, clockwise bending moment, it will bend to the to uh from a position 2. If the bending moment is here, counterclockwise, then it will cause the column to bend towards position number 3. Can you imagine? I hope you can imagine this one. Okay, it will cause the, okay, to bend like this one. Okay, so if the it bends about the major axis, so the longer, the longer side is H. H is the longer side. Okay, and you just remember that Z is the major and Y is the minor axis. And then, okay, how about if it bends about the minor axis of YY? So just similar to the major axis, they say, so this is the YY axis, and then this is the ZZ axis. Okay, and then this is the position of where we sit. This is position number now, sorry, YY, okay. Number 2, number 2. It is number 2 now. So this is number 2, this is number 1, and then this is number 3 is at the top. Okay, number 3, and this is number 4. Okay, so if we have a column here, this is the column. Here is the column, and then we are sitting here. We are sitting here from direction number 2, from position number 2. We are sitting here. We look at to the column. So this is the ZZ now. Okay, so this is this is the ZZ. Okay, this is the direction of Z. There's the axis, and then this is the YY axis. Okay, and then as previous, we have the bending moment, and we will have the axial load of N, and then we have the bending moment. Okay, if the bending moment is rotate clockwise here, so it will cause the it will cause the column to bend to what direction? Okay, let's say this is this one is direction number 4, position number 4, and this is position number 1. So if the bending moment is rotate clockwise, it will cause the column to bend towards number 4. Okay, like this one. Okay, and if the bending moment is rotate counterclockwise, so it will cause the column to bend towards the position number 1. Okay, so you just remember that if this is the meaning. What is the meaning of rotate bends? Okay, bends about minor. Okay, so the minor is the axis of YY is the center, and then it will rotate. Okay, we rotate. This is the center, and it will rotate here, or rotate here. This is the center. Okay, I mean the axis. Okay, the axis is YY. So if the axis is YY, so the shorter side is the H. Okay, just easy to remember like this one. Okay, easier way to remember. If the column bends about major axis Z, H is the longer side. if the column bends about the minor y, okay, the minor axis, h is the shorter. Okay, it's okay. Okay, for the better understanding, let's take a look for the on this plan view. So we have the, okay, let's say the position. Okay, let's take a look on the column B first. Okay, the column B, this is column labeled as B. Okay, this column is having let's say column B is having, okay, let's say this is beam number 1, and this one is beam number 2, and this beam number 3. Okay, the axial, okay, this is the uni-axial bending, okay, which is it will bend only in one direction, bend only in one direction, because it will bend, okay, by the action of beam number 1, it will bend to, okay, this is a position, okay, this is, okay, let's say this is position number, okay, this is position A, B, C, okay lah, this is X, Y, and Z. Okay, by the action of beam number 1, okay, it will, this one, okay, this is the bending moment, and it will deflect, let's say this here, it will deflect like this one, okay, because the bending moment is here counterclockwise, and then this towards Y, okay, this is Y, and this is X. Can you understand? Okay, I hope you can understand this one. This is the action of beam. This is beam number 1. Okay, by the action of beam number 1, it will deflect like this one. Okay, or it will bend like this one. However, we have the beam number 2 here at another side. So here, beam number 2, and the bending moment will be like this one, clockwise, and then it will rotate this one. Okay, so the beam number, the action of beam number 1 is cancelled out by the action of beam number 2, provided that the span of beam number 1 and beam number 2 is not to a similar, okay, similar span, or not too much differ. So the bending towards X or towards Y is cancelled out. However, we have one beam here, beam number 3. So beam number 3, let's say this, okay, by this view, beam number 3 is here. This is beam number 3. It will cause the bending moment like this one. So this is, let's say, X, Y. Okay, let's say the Z is here. Okay, Z is here, so it will bend like this one. It will bend towards the Z. So this is the condition. Okay, this is, let's say, for the first one, major axis. This is the, okay, Z, and this is Y. Okay, so it bend through this one. Okay, it rotate through the Z axis. So Z axis is the major. Okay, we know, as we discussed before, Z axis is this is major, and Y axis is the minor. So it bend about the Z axis, which is major. So the longer span is known as H. This is the longer span is H. Okay, this is important letter for the calculations. Okay, so this is H. The H is the longer. Okay, like this one. Okay, H is the longer because it bend through the major. The major or the minor, you determine. Okay, and it must be fixed. Okay, let's say this is Y and X. However, for number C, okay, similar. Okay, let's say we have the beam number 1, number 4, number 5, and number 6. So the actions, and let's say we have direction or position of J, K, or L here. So the bending towards the J, Okay, I hope you can understand what I'm saying. The bending towards the J and uh, towards the K is cancelled out. Okay, because the loading and the span of the beam number 4 and number 5 is quite similar. So the bending towards the J and K is cancelled out. However, the bending towards the L is occur. Okay, so it occurs. So this is the axis YY. So it will bend through here. So the condition is C here. Okay, the bending is about minor axis. So the shorter direction is known as H. H is the shorter direction. Okay, like given in this rule of thumb. Okay. However, the biaxial bending is for here, column at the corner. Column at the corner will experience biaxial bending because it will bend through the, okay, this is YY. YY is the minor, and this is through the ZZ direction. Okay, we have beam. We have beam 456. Okay, this is beam number 5. Let's say this is beam number 5, and then this is beam number 456. Sorry, this is beam number 7, and this is beam number 8. So, okay, beam number 7 will cause the column, okay, will trigger the column to bend here, to bend along the Y direction. So the shorter, okay, the Y direction, so the shorter shall be okay, like this, the situation of C. Okay, the shorter shall be H. Okay, however, beam number 8 will cause the column to bend here. Okay, to bend around the minor major axis, which is Z. So the longer here, the longer side here is now is H. Okay, the longer side is H, like this one. Okay, the condition of here. So we must refer to the major axis. Okay, major axis, and both. Okay, so this one is from to the major axis is mx, and then the my is here. Okay, my is caused by beam number 7, and mx is caused by beam number 8. Okay, for the situation of, sorry, for the situation in B, the mx here is caused by beam number 3, and my here is caused by beam direction of beam number 6. Okay, so this is the further explanations about, okay, the actual height and the clear height of the column, okay, from the top of the floor, top of the beam to the soffit. Okay, this one we call it as soffit. Okay, soffit is the bottom side of the beam. So this is the clear height is from here to here. In fact, the actual height is from here to here. Okay, this one to this one is the actual height. From the neutral axis of the bottom beam to the neutral axis of the top beam. Okay, in our next video, we will discuss about the examples based from the module. Okay, thank you very much for your attention. So see you in the next video. All the best.